So thanks again to be here on time. Good morning, everyone, again. So this is part 2. Okay, it's working. This is part 2. He has not written part 1, but it's fine. I'm very grateful because he has very clear introduction of what is going on in the interstellar medium and what is the physics that you can find in this environment. But here we will more focus on the chemical evolution from this interstellar medium to what we have in our primitive object, because that's object that cannot be observed right now in other planetary systems, but that's the chemistry we want to have as a complex chemistry we can have in the primitive object. So what we want to trace is how it's going on from this interstellar medium to this kind of primitive object, if we can. So just a bit of me. I was born in the 80s, best decades. I always been interested by nature and so on. I always wanted to be an ethologist, but then, I don't know, I made the path to biology and I end up in chemistry. I did my graduate school in organic chemistry, and then I have a PhD in astrochemistry. And I was very lucky because I did follow the school as you in 11 and 12 for the edition in 11 and 12. And then I did some postdoc in cosmochemistry, planetology. And then I obtained my CNRS permanent position in 18. But I'm not doing mainly astrochemistry. I'm doing also some bat ecology and a lot of spelunking during my free time. I don't have too much free time, but you know. All right, so let's talk about astrochemistry. So for me, astrochemistry, it's the chemistry in space. So it's account for the interstellar medium, but it's also account for the chemistry that you can have in any planetary system. So on Earth, we know that this chemistry has become vital. We have chemistry in our biology, of course. We are made of lots of different molecules that working together and so on. Okay. And so on. So we have chemistry also, as we know, everywhere in our solar system and in the different objects of our solar system. And we will more focus here on the two kind of primitive object that we have in our solar system, trying to understand how complex can be the chemistry in space and how to form it to end up to something that we have in the natural object of our solar system. So let's jump directly to this complex chemistry. And imagine you want to analyze life from a chemical point of view. So for that, imagine you are taking a cell from any living organism on Earth, and you analyze it with what we have the best in the lab is the high-resolution mass spectrometry. The analysis will give us something like that, which is a mass spectrum, okay, from the different molecule that you have in your sample, and it's looking a bit like what Pierre showed us just before. It's a lot of different peaks that it's not, in this case, completely clear. And so from that, what you can obtain, it's each peak will correspond to what we call a formula. A formula, it's contain atoms such as carbon, hydrogen, oxygen, nitrogen, and sulfur, with different indices, following the number of carbon of hydrogen you can have in this formula. And behind each formula, you can have different molecules because a formula can hide different isomers, of course. So if we count the number of peaks attributed to formula in the live sample, we have roughly 3,000 formula. Then what we can obtain also from that, it's the distribution in chemical families. If you have only CHO containing molecule, CHOS, CHNO, CHNOS. And then you can have this kind of pie chart with color code corresponding to this chemical family. And the most interesting for us is this representation where you have the ratio between the H2C and the O2C atoms in each molecules, and you end up with this kind of plot. It's called Van Crevelen, but never mind. What you have to look here is the distribution you have over the H2C ratio and how it's spread on this plot. And what we can see is that you have different sizes for the bubble, and this size corresponds to the abundance of the molecule in your sample. So the bigger is the size, the higher abundance you have in such a molecule. For example, the green one is the CHO containing molecule. So just look at that as a painting, okay? And let's compare that with another sample, which is not life, but it's past life, coming from geological sample, okay, that you can find on Earth everywhere. And this time, the signature is completely different, okay? You have a signature mostly dominated by CHOS molecule. Roughly, it's the same number of formula, but completely another distribution. And as you can see, the pattern here on this H2C O2C plot is completely in the middle, and all the dots have the same size. Okay, you don't have this kind of pattern we had in the live sample, where you have higher abundance of some molecule compared to the other. And we used to compare that with what we call no life sample, and it's a meteoritical sample. So here again, look at the distribution. We have here a kind of equilibrated chemical families with a lot of CHNOS compound, but we have this time 15,000 formula in this sample. So then when you multiply by the number of isomers you can have in a formula, it's 1,000 of molecule more. And here the distribution, again, all the dots have the same size, but it's completely shift towards something with a lower H2C ratio and quite higher, in fact, H2C ratio here. So I wanted to show you this because I want to speak about this meteoritical sample a little bit. So let's see what you have in terms of organic composition in meteorites. So you heard about meteorites the past days, but here I focus only on the carbonaceous chondrite. So it's only one of the primitive meteorites that we have on Earth, and it's the most interesting for us because they contain from 1 to 5 weight% of organic matter. And in fact, they contain already what we call the building blocks of life. They contain amino acid, nucleobases, sugar, and so on. And when you want to analyze this chondrite, usually to extract this organic matter, you are doing that with soluble solvent or with demineralization of the minerals. So from the soluble organic fraction, which is the smallest fraction, you have all this kind of distribution in the organic molecules, with the carboxylic acid being the main molecules, but you have also the amino acid, the sugar, some PAH as well, some aromatic hydrocarbon here. And on the other side, on this insoluble organic matter, which represent most of the mass of the organic matter that you have in this sample, you have more something like a macromolecular structure made of a lot of hydrocarbon, aliphatic and aromatic compounds that are linked together in a macromolecular structure. If we do the same as before, looking at each phases, each fraction with this high-resolution mass spectroscopy, you can recognize the mass spectrum I was showing you before. Here, it's another representation of what we can obtain from this. It's H2C over the mass ratio, the mass plot, but it's the same. We can count the formula we have on this mass spectrum, and we have roughly 11,000 formula. So let's multiply that with the number of isomers, and we end up with like 40,000 molecules in this fraction, okay? We do the same for the insoluble organic fraction, because we can also analyze the insoluble organic fraction with this high-resolution mass spectrometry, and it's quite the same. We have such high number of peaks that we multiply with the number of isomers, and you end up roughly with the same number of molecules in this insoluble fraction. These carbonaceous chondrites are, for me, the best primitive object that we have in the solar system, also because we have a lot of them in the collection on Earth. And here is just the last result they have obtained from Bennu and Ryugu return sample with this high-resolution mass spectrometry analysis that I've just shown you. And this is compared with the Murchison meteorite, a well-known meteorite that has been studied for decades now. And so what they have seen, for example, is that you have less formula in the Ryugu and the Bennu sample. It's because it's not the same class of carbonaceous chondrite. They are Ci, this is a Cm. And then they have seen, of course, some differences in the repartition of the CHO or CHNO chemical family. But what I want here to emphasize is that even these very primitive objects are all rich in organic molecule, but they are all different. And this is completely contrary to life chemical signature that I've shown you just before, with the same analytical techniques, of course. So if we count, we have like 80,000 molecules in this kind of sample. So the question is where this diversity comes from. And we have the same question for the comets. So they are more difficult to analyze because we don't have sample in the lab from comets. And here it was the view, simplified view of the composition of comet we had before the Rosetta mission. So on the top, you have some of the molecule that can be that was observed in the coma of this comet, so mainly volatile molecule, water, carbon dioxide, carbon monoxide, and so on. And it was usually compared to what we can find in the interstellar ices that Pierre showed you, and I will come back on that. After the Rosetta mission, so you know this famous mission from ESA, I won't talk too much about that because I think we will have someone talking about that on Friday. But what they have seen is that in the volatile fraction, you have a lot of different molecules, like hundreds of different molecules, much more than what we were capable of doing from Earth or from space mission before. And in the solid fraction, they have found that you have like a macromolecular structure like the insoluble organic matter in the meteorites. And they assume that this the core of the comet Churyumov-Gerasimenko was mainly half organic in composition. So again, this high diversity in the comet, what is its origin? So of course we have the missing sample because we don't have this comet sample in the lab. We can't analyze it with the high resolution mass spectrometry I was showing you. And the second missing sample is that we need more precise observation of the protoplanetary disk, but as Pierre told you, it's quite difficult because it's so small. I mean, some EU. So what we have what we know from this interstellar medium in terms of molecular diversity, and then we have our primitive object in the solar system. So can we find a way to link these two different environments from a chemical point of view? What we know is that, of course, the matter is recycling in the interstellar medium. So you have, of course, the formation of the carbon from the stars. This is accumulated in the interstellar cloud, in the interstellar medium, can form some simple molecule, and then what we will see is that if we can have the processing of this organic in the presolar nebula and the condensation into what we have in our solar system, the asteroid, the comets, and the planets. And then these could, of course, fall on the different planets, and then at the end of the lifetime of this planetary system, everything will return in the interstellar medium. So let's wrap up just what Pierre shown you before. From what I want to show you here is that, so the interstellar medium, we have these two phases, the gas phases being the main abundant one. You have this hot temperature in this environment. The hydrogen is under the form of atomic hydrogen and not dihydrogen. You have a lot of molecule in the gas phase, and we have these solid grains that can have different sizes that are everywhere. That is the dust of this interstellar medium. And to observe this gas, we are doing that by radioastronomy. And it's been more than 300 molecules identified in this kind of environment. And I just want to emphasize on this hydrocarbon molecule that could be very interesting then for the account of the carbon that we have in our primitive objects. But most interesting for us is the inside of this molecular cloud. Because of this dense environment, you have a very low temperature going on inside. It's where you have the formation of the dihydrogen, by the way, and it's where we have our icy grains. So why these icy grains are very important here for the chemistry, it's because they can become a very powerful chemical reactor. And I will try to convince you about that from a chemical point of view. So this has been shown by Pierre. We have a lot of molecules detected in this environment, but only few of them have been identified in the solid phase because of the limitation of the infrared spectroscopy, of course. So here it's the observation of two different molecular cloud or nebula in the interstellar medium, where you can see that you have absorption, of course, of some molecule that has been shown by Pierre before. And what you can have from that, it's their abundance. And you can see that they have different abundance following the different objects you are looking. But you can do this kind of average composition of this ice in the interstellar medium, and you will end up with this kind of distribution where, of course, the water is the main abundant molecule. You have carbon monoxide, carbon dioxide, then you have a lot of methanol, a lot of ammonia, a lot of formaldehyde, methane, and formic acid. So from this molecule, in fact, you can already start a quite complex and a quite interesting chemistry. Let's see just a bit more how we do this hydrogenation reaction. So that's the first chemical reaction you can do in the low temperature of this environment. And the first molecule to form is water. So what you have in the what you have in this animation, it's in white. You have the hydrogen moving at the surface of the grain, and you have the oxygen in red that are quite stuck on the grain. But when the hydrogen hits an oxygen, it will, at the end, with this kind of reaction, lead to the formation of water. And so, after some time, all your grain will be completely covered by at least water. Because you can also do other hydrogenation reaction. You can have, of course, the formation of the methane. If you saturate the carbon, you have the formation of the ammonia. If you saturate the nitrogen, and you have the formation of methanol from the CO. And then, only from that, it reminds us the distribution, the average composition of the interstellar ice that we have in this cold environment. And what is very interesting from this hydrogenation reaction is that they are almost barrierless or have a very low energetic barrier reaction. So from this ice that are inside this kind of molecular cloud, what we know is that these interstellar clouds are the place to form new planetary system, okay? So if we do this kind of schematic evolution from the molecular cloud to the formation of this circumstellar envelope around the new star, then the protoplanetary disk surrounding the star, and then hopefully to something that looks like our solar system, the question is, do the organic molecules that were present in this interstellar ice evolve? Not only in the interstellar ice, but so I will talk about this as a two-step process. First, from the interstellar medium to the protoplanetary disk dusk, and I will show you the case of this interstellar ice reactor, and then we will talk a bit about what's going on during the accretion and once your primitive bodies are formed for this organic molecule. And I will end up with some implication for the biochemistry that we have on Earth from what we learn from this astrochemistry in space. So to reproduce the evolution of the organic in space, you have three ways. You can do, of course, experiment. It's the thing that I will show you. You can do model and calcul, and you can do observation. But everything is related because you need models to explain some experiment. You need the observation to fit the experiment and the model, and you need the experiment to fit the model. I think I already said that. So everything is related, and it's a very interdisciplinary research in that way. So I will talk to you about the theory of the interstellar reactor as a very powerful chemical process. It's not the only one that can happen, of course, in terms of chemistry from this interstellar medium to the primitive object. But for me, it's the most interesting, and you will see why a bit later. So let's see how can we do this astrochemistry in the lab. So here it's the picture of one of the device we have in my lab, where you can reproduce the condition of the interstellar medium. You can reproduce the very cold temperature of this interstellar medium with this kind of cold head. You have a pressure, it's a high vacuum chamber, in fact, with a pressure that is minus 10 to minus 9 millibar. And you have different kind of energetic sources that can bring you, for example, the UV radiation from a new stars or the thermal emission from the stars. And usually this chamber is coupled to two kind of different analytical tools. It's the mass spectrometry and the infrared spectrometer. So when you have your ice, that it's represented here in the middle of this vacuum chamber in the sample holder that we call the cold finger, it can be so processing with this kind of UV lamp, and it will be followed by infrared spectroscopy, and all the volatile that will go out, that will sublimate from this ice, will be analyzed with the mass spectrometry techniques. So let's see step by step what we are doing in the lab and what's going on for the organic molecule. So the first step we are usually applying to this ice, it's the irradiation step. So it means that we are going to simulate the irradiation of a new stars or surrounded stars, and mainly with UV. But you can do it with electron, you can do it with higher energetic particle. But here it's the picture of the UV lamp that we have. So it's a plasma of hydrogen that we can produce in the lab. And in that case, of course, the energy of this plasma is like 3 or 4 times the energy that what we can have in the interstellar medium, because we want, of course, to accelerate the reaction. We don't have million years in the lab. So we are doing this kind of experiment at low temperature between 10 and 20 Kelvin. So what's going on? Let's see if we start from methanol, which is a quite interesting molecule because it has carbon, it has hydrogen, and so on. If you irradiate this methanol, either by the UV or the electron, you will break this methanol, okay? You will create the radicals and a lot of H atoms. This is represented here from the same animation pseudo as before. So you are in the surface of the grain. You already form your ice and all other of your molecules, and then you have, I think here it's a methanol that's weight. Here it's another molecule that has been formed, and what will appear, be ready, it's a photon that will arrive from here. It hits the methanol, it loses a hydrogen, so it became a radical, and it became reactive, and because next to it, it had another molecule to react, it will form new molecules. So the irradiation broke the molecule, but also allowed the formation of new one, such as, for example, the methyl formate here, the glycolaldehyde, the glyceraldehyde, and so on. And the key here is the formation of these radicals. If you have a too low temperature, the radical won't move at the surface of the grain, but if you have a temperature like 20, 30 Kelvin, it will start to move and have better chance to meet someone else at the surface of the grain. So how to study this radical in the lab? We can see some of them with the infrared spectroscopy. So we can follow their formation. For example, here it's from the formaldehyde molecule. You can see that we have some absorption band corresponding to the HCO radical, but the best tool to study this radical is by electron paramagnetic resonance. So it's quite complicated to have it in the lab, but it's quite powerful if you want to determine precisely the chemical mechanism to form this molecule. And here is some of the network you can obtain from this experiment, from this irradiation step. So here it's an example from Moberg, where you start from methanol, you irradiate your methanol, and you are producing a lot of different molecules. As you can see, the UV is here, and then you have a lot of contribution from the OH, which came from the photodissociation of the water. So the water also play a main role in the chemical evolution of these molecules at the surface of the grain. So of course, irradiation breaks the molecule, but it helps forming new one. The second evolution that could happen for these molecules at the surface of the ice, even at low temperature, is the acido-basic reaction. This acido-basic reaction are forming salts, okay, organic salts. For example, here from the formic acid that I've shown you, it has been detected in this interstellar ices. You have here the ammonia, and you form the ammonium formate. And it's quite easy, and you are forming it even at low temperature. In all our experiments, starting from formic acid, you are forming this salt at 10, 15 Kelvin. And what is interesting is that these salts have large and intense absorption band, which can be interesting, but can be also misleading when you want to attribute this band from the infrared spectroscopy. But the salts, once they are formed, if they are not reacting with something else, they can remain stable until high temperature because they won't sublimate until like 250 and sometimes 300 Kelvin. Here it's the study that show you here the evolution of the spectra for this ammonium formate form at 14 Kelvin and that are still here on the cold surface at 210 Kelvin. So why it's going on? It's because also it's a barrierless reaction, this acido-basic. And it's very interesting for this cold environment. So the key here is not the radical, it's the acido-basic property of your molecule. And in fact, I take again this spectra from the object I've shown you from the interstellar medium. And as you can see here, it has been proposed for the contribution of some bonds like the ammonium behind or with the methanol, like the ion format here, or the OCN minus in the region of the CO and CO2. So they exist and they have been characterized, but not enough because of this infrared spectroscopy limit. So then, usually what we are doing with this ice is that we warm. Once we have irradiate, you can continue to irradiate during the warming and see what's going on. But if you stop irradiation and you warm, you will have two different phases going on in your ice. First, if you warm until 100, 200 Kelvin, you will have, it's here, you will have a lot of chemistry in what we call diluted environment because you have a domination of water in your ice. And so the radical and the thermal reactivity are going on in the water ice. You form small to complex organic molecule, and then from 150 to 185, 190, you are desorbing, you are losing the water. So it means that you are losing completely all your compound from the surface, and you have the main desorption, in fact, of the volatile organic compound at this temperature, and some of the volatile compound can be, in fact, trapped in the water matrix. We know that because some of the molecule that is sublime with this water can, in fact, if they are pure in this in the cold surface, they could have remained until 200 or even more. But the fact is that the water being the main dominant component, when the water is sublimate, you lose part of the composition. But not everything. I say part because then you still have something on your cold finger, and it became even more interesting because in that case you have a reactivity in absence of water in your solid surface, and it's where you have the formation of what we call the macromolecule in this case. So let's see what's going on in terms of chemistry. So you have the activation of some chemical reaction because of the temperature. Of course, you can have a chemical reaction with energetic barrier. Because of this temperature, you can go up to 100 kilojoule per mole for this energetic reaction. And you have a lot of reactivity going there. It's not only a 2-body reaction, it can be a 3 or a 4-body reaction. And it has been studied for decades now. And the main reaction that's going on is between these three kind of chemical compound: the acid, the nucleophile that could be also a base, and the electrophile. And what's going on is that you have this acido-basic reaction that I've shown you, and more are happening with the temperature, but then you have this polymerization and condensation reaction that lead to the formation of this macromolecule. And then the other chemical reaction that is very important with the temperature is this nucleophilic addition. And again, very complicated network, But it's not that complicated. In fact, you can decompose it with hydrogenation reaction, photochemistry reaction, acido-basic reaction, or nucleophilic addition polymerization. And this is what has been done in my lab during the past 15, 20 years. So it looks like it's not that much, but in fact, if you want, for example, to study this kind of reaction, like formaldehyde with ammonia, it took me, during my PhD, more than 2 years, okay? Because it's very complicated to be sure of the analysis that you have from your infrared spectra, and that you have to, of course, repeat the reaction and try with other compound to see if it's not that mechanism that was going on. And what could be interesting from that, so you have all this chemistry here in blue going on in the water matrix, and you have all this chemistry in light yellow going on without the water, because you have this here, the water sublimation. And so some of the molecules that you can produce after the water sublimation could be used as thermometer of the ice if we were able to see precisely this ice at different temperature in the protoplanetary nebula, for example. So here it's a video of our cold finger in the lab, where you can see here you have the ice and then it starts eating. So you have bubble forming at the surface because you have the sublimation of the compound. So here you have it was very fast because of the water sublimation at one time. But then you still have a lot of things at the surface of the window. You still have some bubbling here. And at the end, we still have something on our support. At the beginning, it was thinking to be something that it was dirty, so it was clean by the colleague. But then we realized that it could be very interesting to analyze this residue, as we call it, the residue of organic matter that has been formed from this process. So the process is quite simple and quite straightforward. It's linear. We irradiate at the beginning, we heat after that, and we sublime the water, and we keep heating until room temperature. So it's not going on, it's not that's going on in the interstellar medium. When you think about this circumstellar envelope and the protoplanetary disk, of course, you will have reformation of ice, re-irradiation during the process and so on. But still, if we do this simple evolution, you have at the end this residue. And what is interesting from this residue is that first, it's completely soluble in water or methanol, so polar or protic solvent. So here it's the view of the cold finger that we have extracted from the high vacuum chamber. And this residue here, its signature by infrared spectroscopy. And as you can see, if you are used to infrared spectroscopy, is that it's something very complex. Only 2 molecules has been identified in this residue. It's this HMT, hexamethylene tetramine. I've shown it to you before in the very complex network, but never mind. And the other one, it's the POM. It's a polyoxymethylene compound. It's a polymer. Why we can identify only these 2? Because the bands are broad and because they can hide a lot of different molecules. So what we can observe, what we can identify from this kind of spectrum is only what we have, it's only the chemical function. So we have a lot of ester, of amide, we have some carboxylic acid function, but that's the only thing we can say from this in situ analysis with infrared spectroscopy. So to go further on this residue, what we can do is to extract it from the device, and here is the window that we extract And on the surface, you can still see the residue. As I told you, it's completely soluble in sample, so we can recover the residue in methanol without sample degradation, and we do this high-resolution mass spectrometry. Comment again. And so here it's the mass spectrum we obtain from the residue, and here, now we are used to it, here it's a plot of the H2C over O2C ratio of the distribution that you have, the molecular distribution that you have in this residue. So it's quite a lot of molecule. In fact, if we count, we have like 10,000 different molecules in this residue. Just to remind you, at the beginning, we usually have 3 molecules, water in main abundance, methanol, and ammonia. So from 3, we end up to 10,000. Very powerful chemistry going on. Very powerful and very diverse. If we go further in the analysis of this residue, we can do targeted analysis with LC and GCMS. So it's chromatography techniques that can help us to know if we have precise molecule, and indeed we have some. We have molecules such as some nucleobases in the residue. We have a lot of sugar. We have amino acid, and even some dipeptide has been proposed in this kind of residue. So you have already all the bricks of life in this residue, and we are not even in the primitive body yet. So it's why this interstellar ice residue theory, it's quite interesting for us. It's because you already form everything you have, not completely the same, of course, but everything you can find in these primitive bodies. So I don't know why there is stuff in there. Anyway, so the theory of the interstellar ice reactor is very interesting because at the end you have this residue that could be an analog of the organic matter that you could find in protoplanetary disk. And if it is, then we can do the comparison, we can do the similitude with the primitive bodies of our solar system. And so we will move from my part 1 to my part 2, and let's see what's going on in the parent body of these primitive bodies. Let's focus again on this carbonaceous chondrite. So you know now they contain a lot of different organic molecules. They are also made, of course, of a lot of minerals, which represent more than 95% of their composition. They are most primitive. Some contain some methane, some metal, and so on. But what we know now since, 50 years from the analysis of this object is that they are not that primitive. They are not that primitive because they all have suffered of what we call secondary alteration processes that could be ranged in two main parts. The first one being the aqueous alteration and the second one being the thermal metamorphism. Here I'm talking only about the carbonaceous chondrite, and we will even more focus on the Ci, Cm, Cr chondrite. That's the one that contains the most abundant carbon. And all of them, indeed, have suffered from what we call aqueous alteration. This aqueous alteration, it's not an ocean that works on this parent body. It's not a river. It's fluid that may have flow along some cracks or something like that, or even in a local environment. But in any case, they have changed, modified, and formed new phases in this parent body. And we know that from the mineralogy, of course, because in this object you have a lot of phyllosilicates. So you have a lot of hydrated minerals that could be only formed during aqueous alteration. So in fact, for the organic matter, we have we can propose also that we had some evolution. So if you consider that at the beginning you had this initial asteroid that we don't have anymore in our solar system, because we have here the current asteroid and something happened between the two of them. Of course, we have pieces of this asteroid in the lab. So the question is, what was the initial organic matter and how we end up with this organic matter that we have now analyzed in this natural object? The second question is, could it be related to ice, to the interstellar ice's evolution, and what is the influence of the minerals, because you have most of the composition here that are minerals in this asteroid. So this can be done by analyzing natural objects. Of course, we have a huge collection of meteorites in the lab, so you can look at this aqueous alteration effect on the natural object, and then you can do, of course, some experiments. If you are tracking this aqueous alteration from natural objects, here is some of the stuff you can do. You can do it on the soluble organic matter, looking, for example, at the speciation of the amino acid, it's very small, sorry, of the amino acid that you can have following the scale of aqueous alteration. So, for example, what we see clearly here is that the black bar represents what we call the alpha amino acid. That's the first one to be formed from aqueous alteration reaction, in fact. And then the more you have this aqueous alteration, the more you destroy this alpha amino acid over something that is more complicated, like beta, gamma, or delta amino acid. So this is stuff that you can learn from the object. And for the insoluble organic matter, you can do the same. You can follow the different aromatic or aliphatic compound that you have in your structure. You can follow the loss of some heteroatoms, such as nitrogen or oxygen, that could be in your insoluble organic matter, following the different aqueous alteration degree. But what we don't know, the main issue with these studies, is that we don't know what we had at the beginning. We don't know the sources and the composition of the organic matter we had at the beginning. So we don't have the starting point. We have only the evolution from something that has been already altered to something that is more altered. Because we don't have also in the collection a carbonaceous chondrite that has not been altered. Every carbonaceous chondrite has been altered, even with a low degree of aqueous alteration, if we believe in the classification of this object, but they all been altered, and the aqueous alteration is going very fast on the organic, and I will show you how. So here we are doing experiment in the lab, and we are trying to follow our idea that we could have this continuum between the organic form in the interstellar medium to what we could find in primitive objects. So you start from the interstellar ice residue, the bottom line of the end of the line of our interstellar ice processing, and we will try to reproduce what's going on in the asteroids. So for that, we reproduce, of course, the water alteration. We try different temperature. You can try, of course, to be in an anoxic condition. You can try to have or not have minerals. You can play with the pH. You can play with the time. You can play with the water-rock ratio. We can play with the fugacity of oxygen. You can play with many, many parameters. That's the difficulty of this kind of experiment. But the main importance, in any case, it's the presence of liquid water. Because here, from our interstellar ice residue, we were always in the solid phase reaction. So from the solid phase reaction, you already had a very interesting chemical reaction going on, and then you take your residue, you put it in aqueous condition, and of course, it will evolve. So then if you apply one of these different conditions, it will evolve differently. So you have to play with all these parameters and to perform experiment, to repeat experiment, and so on. And so here it's one of the experiments we have done in the lab. So now you recognize the pattern of our residue with this high-resolution mass spectrometry techniques. This residue has been submitted to hydrothermal alteration at 150 degrees Celsius in anoxic condition for 100 days. And this is what it became. So everything has been redistributed, and in fact, none of the molecules, none of the formula that we had here are here. Everything has been transformed, everything has been reprocessed, and you lose, as you can see, we lose part of the oxygen, we decrease the H2C ratio, and we end up with something that is more compact and more in this region. In terms of number of molecules, we keep the same. We had 10,000 molecules at the beginning, we have 10,000 at the end. So the diversity remained the same, but the distribution, the molecular distribution completely changed. And what we can do then is to compare this molecular distribution with the one that we have in the soluble organic matter of meteorites. So here, it's only the soluble organic matter in terms of CHNO and CHO molecule, because that's the only molecule we have in our residue. And as you can see, we will not compare in detail the molecule in terms of formula. Do we have the same formula here or here? That's not the point. What we can see, however, is that when you do this process, you are reprocessing your entire molecular distribution to something that is more looking to what we have in the natural object. But in terms of number of molecules, we are 4 times lower in our residue, because in this soluble organic matter, you still have your 40,000 molecules. But it doesn't matter. no. But in any case, it could be a contribution. The ice residue, the residue could be part of the contribution of this soluble organic matter that came from the interstellar medium to the primitive bodies. That's a hypothesis, but a likely hypothesis. So I've just shown you this evolution of this interstellar grain, but of course, in the primitive bodies, it was not the only source of organic matter that you could have. And I just want to focus a bit, on another sources of organic matter you could have, and that could have been formed in the protosolar nebula itself from plasma reaction at the border, so here. I want to focus on that because it's a very interesting analog that you can form in the lab, and it's also something that is very diverse. It's called the nebulotron. It's formed in the CRPG, so another lab in France by colleague, and they are doing this gas mixture of CO, H2, N2, submitted to a plasma discharge. So you can see here the plasma discharge of this gas. It's not the same color as our hydrogen plasma, if you remember, because we have CO and because we have N2 in the mixture. And when they stop the experiment, they are producing this kind of dark brownish matter that under the microscope looks like fibers, filament, and has this very rich carbon composition. And if we look at this with the high-resolution mass spectrometry, here is some of the results they obtain. So in terms of nitrogen abundance, because you can play with this N2 gas that you are introducing in your mixture. And so they have shown, for example, that the number of formula raise to something that is twice the number if you have more nitrogen. It's because the nitrogen is incorporated in the structure, in the macromolecular structure, and you can do some better, let's say, bonds with nitrogen compound than without. But what is also interesting is that compared to our soluble organic residue, this kind of analog is mainly insoluble. So what it means that it could be related to the insoluble part of the organic matter that you have in the carbonaceous chondrite that we do not reproduce with our interstellar ices. And they have indeed do this kind of plot where you have only the H2C and the O2C ratio of the nebulotron analog compared to what you have in the insoluble organic matter of meteorites. And then, of course, the primitive bodies, during this aqueous alteration, you also had some organic molecules that have reacted with the minerals. So this is a microscopic image of the matrix of CR meteorites, where you can find this phyllosilicate sulfide mineral compound that is very close or mixed with some organic matter. So the organic matter, this organic matter can be found as globule, like as represented here, as separate, let's say, place than the minerals, but you have also a lot of signature of organic matter with the mineral, and particularly with the magnesium phyllosilicate that you can have in this object. So if we believe in the interaction of the organic with the minerals that you can have in many environments, this is a schematic view of the different interaction that you can have between the molecules and the minerals coming from soil study. You have, so everything, in fact, is dependent on the nature of the organic and the nature of the minerals. So it has been applied to chondrite quite recently, but it's only the beginning. And what you have to keep in mind also is that at the beginning of this hydrothermal alteration, we had primary minerals that were not under the form of phyllosilicate. So while the minerals were transformed, the organic were transformed as well. So you will have a very intimate relation between the two phases during all this process, and maybe end up with the more polar compound stuck with the phyllosilicate, leaving behind the more insoluble or hydrocarbon compound as a globule in this kind of organic matter grain. So imagine if you have to experiment all the different reactions you can have between the thousands of molecules we have in this object and the 100 different minerals we have in this object as well. It's a nightmare. But we are doing it. So just to finish with my presentation, I want to go in application of this very diverse and complex chemistry you have in this kind of object, and try to link that with the biochemistry we have on Earth. So now you know space is not an empty space devoid of organic molecule. It's full of organic molecule. The abiotic synthesis there, it's very easy. And so even if we don't know how much of this primitive object could fall on the different planets and have fall on Earth, of course, everything that has been formed inside these primitive bodies could have fed the planet even before the formation of the planets. And I've not the time to speak about the chemistry that you can have in different environments, like Titan or Venus, but of course, abiotic synthesis there, it's also very efficient. Maybe as much as in the interstellar grain. What I want here to emphasize is that if you remember my first presentation of this plot of life, no life, and past life, you have a clear difference between the abiotic chemistry and the biochemistry. And in terms of formula, you have seen that we have 3 to 4 times less molecule in the biochemistry. So it means that maybe we could have a selection if we start from this extraterrestrial matter. So what you can do is to separate this complexity to the diversity, which is not the same when you speak of a molecule, and you can draw what's going on from our interstellar ice to what I call a culmination of abiotic chemistry, which we found in meteorites. So what we have seen right now is that from the interstellar ices, where you start from 3 molecules, you have a huge increase of diversity, as well as the complexity, but it is not the complexity that we have in biochemistry. Even if we have thousands of molecules in this sample, it's not as complex as the biochemistry we have on Earth. And so we could have this kind of path, trend, between the abiotic chemistry, that the culmination of that we have in the primitive bodies, and the biochemistry that we have on Earth, only by decreasing this diversity, as we can see from the analysis here. And so in between, we can think about a transition zone that could be what we call the prebiotic chemistry. This is the trend from what I've shown you, okay? From the chemical evolution I've shown you. But what about another one? Another one where we don't need to go to this culmination of abiotic chemistry, where we don't need to form such diversity, and we will increase the complexity and go directly to the biochemistry we have on Earth. In that case, if we believe in the strength of abiotic synthesis that could form many diverse organic molecules in many environments, what you need here is to constrain your chemistry by different conditions coming from the environment. You need to avoid the abiotic chemistry to take place, to have something that is selected and something that is constrained to keep the low diversity and go towards more complexity with time or with the process. So, finding amino acids, finding any sugar or any other molecules that you could analyze in this extraterrestrial sample is not a sign of life, really. And it's even not a sign for us of chemical complexity, because an amino acid is not something complex. Which is complex is the protein that you could form from the polymerization of this amino acid. And it's the same for the sugar or the nucleobases that you have. It's not a complex molecule. What is complex is the DNA. So we can't from what we know now, we can't claim any life signature until we have experiment and observe all the possible abiotic chemistry you could form in any astrophysical environment. And I think this is the most important message I want to give you. And I will finish with this open question. Based on that, what is a biosignature? And especially if you look beyond the Earth. And I've done.